Hi, in this video I'm gonna review the fluid statics and also solve three problems. So the fluid statics is when the fluid is either at rest or there is no relative motion between adjacent molecules. Also, there will be no shearing stresses in the fluid, and the only forces that develop on the surfaces of the particle will be due to the pressure. Pascal's law says that the pressure at a point in a fluid at rest is independent of direction as long as there are no shearing stresses present. Also, there are two different forces acting on an element. One is the surface forces that only act on the surface of the element, which the examples of it is pressure and shear stress, and the other one is the body forces, that those forces are acting on the body or the volume of the element, which is the weight, and also the forces due to the electromagnetic fields. The fundamental equation for fluids at rest is that the dP over dz is equal to minus gamma, where P is the pressure, Z is the elevation, and gamma is the specific weight. And for incompressible fluid, we can write it as the pressure difference between 2 points divided by elevation difference between those 2 points is equal to minus gamma, which is the specific weight of the fluid. For example, here this point is point 1 and this is point 2. So we can write this equation as the pressure difference between those 2 points divided by Z2 minus Z1 is equal to minus gamma. And we can see here that we can call Z2 minus Z1 as H. So here this equation would be equal to P2 minus P1 divided by H is equal to minus gamma. Or we can write P1 is equal to gamma H plus P2, where H is the depth of the fluid measured downward from the location of point 2, and H is measured from the free surface here. And this is the sign of a free surface. And the measurements of pressure, one is the absolute pressure, which is measured relative to a perfect vacuum, and the other one is the gauge pressure, which is measured relative to the local atmospheric pressure. And the relation between these two is given here, where the absolute pressure of any point would be equal to the gauge pressure of that point plus the atmospheric pressure. So we're going to solve three problems here. The first problem says that the closed tank contains compressed air and oil with a given specific gravity as is shown in figure, and a U-tube manometer using mercury with a given specific gravity is connected to the tank, and the column heights are H1, H2, and H3. It says determine the pressure reading in PSI of the gauge here. So in order to solve these kind of problems, the problems that the fluid is at rest and it's not moving, we need to write the manometer equation between 2 points. And those 2 points, we have to know the value of pressure at those 2 points, or all the gamma and H between those 2 points. So for example, we can pick here point 1, and this would be our point 2. So here the value of pressure at point 1 is what we want to obtain. Then the value of pressure at point 2, since it's open to atmosphere, its absolute pressure would be atmospheric pressure, which means that the gauge pressure at point 2 would be 0. So to write the manometer equations, we start at point 1. So the gauge pressure at point 1. So now we are here at this point. So we will move toward the other point, since the as long as the fluid is not changing. So we have to move downward here, then we move to the right, then again we move downward, but at this point the fluid changes, so we stop. So here we move downward, to the right, and downward. And as we said, H is evaluated from the free surface, which would be here in this problem. So as we move downward here, since H increases, so pressure will increase as well. So it would be plus gamma of the fluid that we have moved through, which is oil, times the distance that we've moved, which is H1, times H1. Now we are at this point. From here to this point, gamma is constant because the fluid is still oil, and also H is constant, so the pressure won't increase or even decrease. So pressure is constant along this straight line. So at this point, when we move downward, again, as H increases, the pressure increases as well. So it would be a positive sign. Gamma of the fluid that we're moving through, which is oil, times the distance that we have moved, which from here to here, the distance is H2, times H2. Now we are at this point. So again, we will move toward our points until the fluid changes. So we have to move downward, to the right, and then upward. So we've reached our point. But remember here, from this point, as we move downward, the pressure would increase. But the increase in pressure in this part will be cancelled by the decrease of pressure in this part, since here and here has the same elevation. So we can draw a straight line here and say that the pressure at this point is equal to pressure at this point. So now we're here. As we go upward, H is decreasing, so pressure will decrease. So the sign would be negative, minus gamma of the fluid that we're moving through, which is mercury, times the distance that we have moved, which from here to here would be H3, times H3 would be equal to the pressure at point 2, the gauge pressure at point 2. So as we said, gauge pressure at point 2 is equal to 0 because it's open to atmosphere, and its absolute pressure is atmospheric pressure. And the gauge pressure at point 1 is unknown, and we want to obtain it. And the specific gravity of oil, the specific weight of oil is the specific gravity of oil times specific weight of water. And also the specific weight of mercury would be the specific gravity of it times the specific weight of water. So from here, this is given as 0.9. Gamma of water is known. The value of H1, H2, and H3 are all known. And also the specific gravity of mercury is given as 13.6. So we can easily find the value of gauge pressure at point 1. Then the next problem says that the closed tank of this figure is filled with water and is 5 feet long. So here we have 1 foot of air. The pressure gauge on the tank reads 7 psi, and for part A it says that determine the height h in the open water column. So again, to solve it, we need to write the manometer equation between 2 points that we have the most known variables there, or we have the value of the pressure at those 2 points. So this would be our point 1, and here would be point 2. Again, we will move from point 1 to point 2 until the fluid changes. So here we have to go downward, we move along this straight line, and then we move upward, down, to the right, up. So now we can write the manometer equation, the gauge pressure at point 1. So from here, as we move downward, the pressure will increase. So plus gamma of the fluid that we're moving through, which is water, times the distance that we've moved, which here is 2 feet. So as we move along this line, the pressure is constant because the specific gravity of water would be constant, and also H is constant. Then from here, from this point, as we move upward, since H decreases, the pressure would decrease as well, so it would be a negative sign, minus gamma of the fluid that we're moving through, which is water, times this distance, which is H, would be equal to the gauge pressure at point 2. And as we know, since it's open, the gauge pressure at point 2 is 0. And here we have the value of gauge pressure at point 1 at 7 psi. We have the specific weight of water, and also so we can easily find the value of H. But the only thing is that here the gauge pressure at point 1 is given as 7 psi, which is 7 pound over square inches. And since here we have 2 feet, we have to convert inch squared to feet squared, so the conversion rate is 144. Each foot is 12 inches, so each square feet would be equal to 144 square inches. So H would be obtained from part 1. So in part B, it says that determine the gauge pressure acting on the bottom tank surface AB here. So in order to find that, again, we have to write the manometer equation between 2 points that again we can use here as point 1, and this is our point 2. And also, since we know the value of H now, we can write it from this point as well. We can write like this, or we can go from point 1 to point 2. So again, as we move from point 1 to point 2, as we move downward, the pressure will increase. So the gauge pressure at point 1 plus, since we move downward, it increases, gamma of the fluid that we're moving through times the distance that we've moved, which is 4 feet, then would be equal to the gauge pressure at point 2. And again here, remember that again for the gauge pressure we have psi, and here we have foot, so we have to do the conversion rate. And for part C, it says that determine the absolute pressure of the air in the top of the tank if the local atmospheric pressure is 14.7 psi. This A stands for absolute. So again, the absolute pressure at point 1, as we know, is equal to gauge pressure at that point plus the atmospheric pressure. So the absolute pressure would be equal to gauge pressure, which is 7 psi, plus the atmospheric pressure, which is given as 14.7 psi. So this is solved as well. The reason that I chose this problem is to show you that this shape of the tank is not important, and the only thing that we care about is the vertical distance for H. And the last problem says that the U-shaped tube shown in this figure initially contains water only. A second liquid with specific weight of gamma, which is less than water, is placed on top of the water with no mixing occurring. So gamma is less than specific weight of water. And it says that can the height H here of the second liquid be adjusted so that the left and right levels are in the same height? Provide proof of your answer. Again, we have to write the manometer equation between 2 points that we know the pressure at those points, or at least all of the variables between them. So here again we start at point 1, we move towards point 2 until the fluid changes. So from here we have to move downward, and we need to stop there because the fluid changes. So we write the manometer equation, the gauge pressure at point 1. Since we have moved downward, so the pressure will increase, plus gamma of the fluid that we moved through, which is simply gamma, times the distance that we've traveled, which is h. So gamma times h. Then from this point we have to move downward. Then we move along a straight line. Then we go up to reach to point 2. Again, similar to the previous problem, the pressure increase along this line will be cancelled with pressure decrease along this line. So the pressure at this point would be equal to the pressure at this point. So we will move from here to here, and as we move upward, the pressure would decrease. So minus gamma of the fluid that we're moving through, which is water, times the distance that we've traveled, which is h, would be equal to the gauge pressure at point 2. So since these 2 points are open to atmosphere, so the gauge pressure at both 2 points are 0. So it would be gamma h minus gamma of water times h is equal to 0, and these two h's cancel each other out. So this yield to that gamma must be equal to gamma of water, which is not what we had assumed. So this is not possible. And also remember here again that the value of pressure is not dependent on the diameter of these 2 tubes. And please don't forget to subscribe to my channel. Thank you.